4.1, number 30. Again, the question is very verbose, and I'm not going to write it the whole thing, lest I spend too much time writing it. So, again, I'll say over the important parts and try to construct a picture. It's useful. They actually have a picture for this one already. I'm just going to redraw it here to help me and try to fill in the most important features. So a trough has ends shaped like an isosceles triangle. So I have a trough. Looks like an isosceles triangle. Isosceles means what? Two sides of the same length, and the third one is not necessarily. And we have some values for these parts. We know that the width is 3 meters. 3 meters there. And the height overall is 4 meters. And the length of the trough, this is just a cross section of the trough really, so the length of the trough, not to scale, is something like 10 meters. All right, 10 meter length, fine. There's water in here somewhere. Okay, that's good enough. And yeah, the front's transparent for some reason. And let's see, water is pouring in at a rate of 5 meters cubed per minute. Okay, so we have, here, wonderful. All right, the water's pouring in at a rate of 5 meters cubed per minute. All right. What is that 5 meters cubed per minute exactly? Well, it must be the change in the volume, right? It's meters cubed. It's a volumetric measure over time, right? So this must be the change in volume over time for the water in the trough. Right? Regardless of what shape the water comes in once it enters the trough. I know when it enters the trough, it's going to flatten out, you might say, into a prism-like shape, right? But nevertheless, the change in volume is always 5 meters cubed per minute. So we can say that that's what the change in volume is with respect to time for this problem. It's an increasing of 5 meters cubed per minute. So dV dt is 5. And it says we're supposed to find the rate at which the height of the water changes when it's 1 meter deep. So if I label the height of the water here as h, right, then according to our notation, the question is telling us to find dh dt, how the height of the water is changing when water is 1 meter deep. So I guess it means h is 1. So it looks like we're supposed to be finding, if we're using related rates ideas here, some relationship between V and H, between the volume of the water and the height of the water here in the trough. And then once we have that relationship, taking derivatives will give us the related rates between the two derivatives of V and H. All right, so let us now search for that relationship to start with. I think an obvious one is probably just let's write out the volume of the water as a formula, right? So V itself, right, not the change in the volume, but just the volume itself, should be able to be expressed in terms of H because it looks like it's a triangle, right? A triangle, and then extended out this way 10 meters. Right? So whatever the area of this triangle is times 10 is certainly the volume of the water in the trough, right? So I'm going to introduce a new variable now. I'm going to write b here for base. Okay, so the base of the triangle, right? I know it's coming at the top, but conceptually it's the base, right, of this triangle here. So there's the base of the triangle. I'll just mark my triangle here. Maybe I should have used blue for the water, but nevertheless, there we are. There's my triangle. The base is the top part, and the h here is the height of the triangle, and therefore the area of this triangle should be 1/2 base height, right? So 1/2 b times h, and then if I multiply that by 10, right, that would give us the full volume of this water, right? This is just the area of one cross-section of the water, you might say. So multiplied by 10, we'll extend it this way through the length of the trough, giving us the full volume. There's the volume of the water at any time t. You'd calculate the base and the height, and you could find out what the volume of the water is for any given time. All right, now that we have that, we want a relationship between v and h, and this variable b here is posing a small problem to that because b is also changing with time. The base is changing with time, right? The water gets higher, the base gets wider, right, as the water fills the trough. So b is a changing component here, and it has a derivative as well. So this is of concern because we don't have anything known about the rate of change of b. We're trying to find the rate of change of h. We know the rate of change of v on the left-hand side. We know nothing about b. Right? This is a problem we have to deal with.